So getting started with ROS, where's the best place to go if you're interested? Go to ROS.org, of course. And one of the primary links, of course, is getting started with ROS. And I would certainly do the installation. I would recommend Ubuntu. If you're brave, you could try some of these other distributions. You can do it on OS 10 on a Mac. Windows really only has client support, not master support yet. But Ubuntu is really the easiest way to get started. And then run through the tutorials. And I say run through them twice. I did. You don't have to. A lot of people here are a lot smarter than I am. But I found that, again, simply the familiarity. I found that simply the familiarity of the terms really made all the difference in the world. So once you start just thinking about services and topics and message passing in the way that you might think of just looking up a value in an array, it becomes very easy. And one of the things that the tutorial is very good, or somewhere in the tutorials is an explanation of the transform frames using two turtles. And that one can actually turn your head inside out for a little while, but then it actually starts to click, and it's really pretty cool. I'll just name some of these. This, again, is just name recognition, and so if you see them once here, you'll see them again next time you go to the ROS.org site. But ROS comes with a bunch of really nice little command line utilities, ROS launch and ROS run and ROS node. ROS launch is the way you may wonder, how do you keep track of all these nodes that are independently and asynchronously commanding your robot? Because normally one would just run one program and everything goes. And the answer is a launch file, which is just a simple little text file with one line typically for each node that you want to run, but then it's all there in one file. And if you want to change one of the nodes, you just change that node specification in the launch file and relaunch the whole launch file, and it does all the node launching for you. ROS topic, at any point in time, you can list all the topics that your various nodes are publishing messages on, and you can also echo the values of those messages at any time. So it's a really good debugging tool. ROS service does the same thing. Parameter server, we'll just buzz through this. RViz is the visualization tool. ROS WTF is just my favorite name of a command. And then the TF echo monitor and view frames are for sorting out all those complicated transformation frames, especially when you have a multi-jointed arm that you're trying to control. RxPlot and RxGraph are kind of neat. RxGraph we already mentioned. This is what gives you that neat little connected line picture of the nodes that you're currently running. And RxPlot actually lets you plot a two-dimensional timeline of different values. So if you are curious about what a particular sonar value is really reporting, and you don't want to just look at a stream of numbers going by the screen, in real time while your nodes are running, you can plot it out on a nice graph, and you'll see immediately whether or not there's noise blipping in the middle of it or something like that. Yeah. Yes, I should have pointed it out. In the installation when you follow the installation instructions on the ROS.org site for Ubuntu, you have a couple of choices of which sort of, how much of ROS you want to install all at once. And if you've got lots of disk space, just go for the whole shebang. And it's basically a bunch of Debian packages that from that point forward are totally managed by the update manager. So they'll be updated when the ROS folks push updates. It's really easy. So yeah, and these utilities here are part of the very basic core package. So these are never not there. It's only later when you're looking at third-party packages that you tend to need to look outside of that basic distribution. For ARM, I don't know. No, not at this point, apparently. And all those little things I just listed are on this ROS cheat sheet, which I actually didn't catch the first time around until I was preparing this little presentation. I wish I had it a long time ago. So right on the very first getting started with ROS is this really nice little printable cheat sheet. It's got all those basic commands, including the things you can do with them. So because sometimes the argument lists are a little strange. So you can print that out, stick it on your monitor, and you're ready to go. so that was a nice segue into packages. So the way that you get ROS software, it's all open source, as was mentioned, and you can typically get it. Well, you get all the basic ROS libraries, of course, just by doing the initial install. But then you'll find all sorts of third-party libraries that you might want to use for your particular card, for example. And how do we get there? Oh, here we go. And so packages are defined as a collection of nodes that someone's providing. There's a manifest file, and there's a command called ROSmake that will just automatically build all the files in the package that person's providing, as well as any dependencies that package may rely upon that you may not already have. And it'll go out and get them and then install them for you. So it's pretty hard to go wrong there. And the most typical way to get packages is using SVN or Git. And I've used both. I'm more familiar with SVN, but some packages just use Git. So you need to learn a few commands for pulling in these packages. But once you do, then you can update them at any time and rebuild them at will. And if you want to contribute back, or even just start your own, and this is what I do, even if you're not, for the first couple of months, I had nothing to contribute, that's for sure. I was just playing. And but I was putting all my code on a Google Code piece of free space on Google Code, which supports SVN. So it's very nice. I use Eclipse as an editor, which has a nice project manager and built in it. Well, you can get an SVN module for it. And what's nice about that is you can sync up your own code repository as you're building code to the SVN site on Google Code, go to a completely different Ubuntu machine, and just SVN it back all to that machine, and you've got basically the same identical code environment. But this is also typically the way that people share their repositories. So before we look at a couple of things higher up, like SLAM, just in terms of some demonstration videos, I wanted to show you this one thing, because again, this is much more appropriate to the hobbyist level. If you don't happen to have a laser scanner, which tends to be fairly expensive, although now with the Kinect, there's the possibility, of course, of doing SLAM visually using essentially a slice of that 3D vision map as a pseudo laser scanner. And I think, again, it was Tully. Was it Tully that wrote a nice laser scan utility, which maps the Kinect output to a kind of a fake, it's not a fake laser scan, but, well, it's fake because it's not laser, but it maps into a laser scan topic, so you can use it in SLAM as if it were. And I guess the only downside is that it doesn't have a huge angle of a field of view. But in any event, before I was able to get a laser scanner, Mike Ferguson at Albany figured out a way to use a panning IR sensor in ROS, and that's all this little video shows. Here we go. Because this is something you could try right away without any need to buy a Kinect or a laser scanner. And so we have a split screen. On the left is the real robot, and on the right is the RViz view of the robot. And I don't know if you can see it, but at the bottom of the robot near the front, there's a little panning IR sensor. And as it picks up obstacles, you can see it places those obstacles in the map in RViz. And what I'm doing is giving it little discrete commands to go right there with the green arrow. I say, come all the way back around here. But then ROS and the path planner has to figure out how to do that without running into the obstacles that it's already recorded. And again, that's something you get for free. The planner is doing some kind of a wavefront analysis or something of that nature, and it gets itself around the obstacles. And as it goes, of course, it updates the occupancy map as the panning IR scanner picks up more objects. So here's one of the advantages of having an RViz model of your robot. Is you see, even as the robot was completely out of sight, we were able to actually still see the virtual robot and know that it wasn't in trouble. I'm just using odometry. In fact, there's no SLAM in this at all. This is just dead reckoning with obstacle avoidance. And Mike Ferguson did try to take it that next step and do proper SLAM with G-mapping. And he said there just weren't enough data points per scan. You're only getting 30 data points per second with these IR scanners, and that just wasn't enough to get the registration. So now this is real slam with the laser scanner. And what I'm going to show you is a very fast rendition. This is 6 times speed. I was running the robot slowly just because I didn't want it to take out the cats or the walls or anything. So I ran it for about 5 minutes, starting in the dining room, through the living room, into the hallway, and then the kitchen. And then once it was done mapping out that region of the room, I was able, just like Tony was saying earlier, just to point to any point in that room, and it could get there on its own. So I'm not sure we're seeing it. Oh, there it is. So let's go back to the beginning. So what's important to show here is that the initial map is just blank. It has absolutely no knowledge. And then as it spins around and starts moving about with its laser scanner and detecting obstacles, the black lines are areas where it thinks there probably really is a wall. And the red is definitely occupied, and the yellow is probably occupied. You can see, again, that took place over 5 minutes, so this is taking place only over 1 minute. But within a very short order, it now has essentially a physical map of a dining room, living room, kitchen, hallway, and even a little foyer up there in the upper left-hand corner. At this point, I can now give it a fairly long-range goal. It's hard to see the big red-green arrow that I just clicked, but he was able to come all the way from the foyer back to the middle of the dining room. So, or once there's the automatic Monte Carlo localization, the AMCL, which does localization when you have a map, and then there's G mapping, which is what I was using here, which is actually building the map from the data at hand. And you can save that map and give it a label and use it at a later time. One of the last things I want to talk about is the frame transformation, since this is what got me, what pulled me into ROS in the first place. And so this is frame transformations the hard way, and this is I did it a couple of years ago. And of course, if you want your robot to reach for an object, this is my goal. I wanted it to do head tracking of a colored object, in this case a balloon. And at the same time, I have a little sonar sensor on the head of the robot that gave me the Z coordinate out to the balloon. So now we had the 3 dimensions of the object in space, and I wanted to move the arms into position so it could grab the balloon. So that's the inverse kinematics problem, and I wanted to solve it just for 2 degrees of freedom, and it's been done a million times, and all it requires is high school math. But the problem is it requires a lot of high school math, and you got to do all these matrices, and there's sines and cosines out the wazoo, and I'm not very careful when it comes to these things. And so I probably spent 2 days just randomly changing sines and cosines until the arms moved in the right direction. It's just because I lost track. So Tully has saved every roboticist on the planet the agony of doing this ever again, and and I'll show you how that works. Oh, but I do have to show that I was at least mildly successful. So this was back in the old days. And it's also just a slide to show that, or a video to show that, yes, you can program robots without ROS, of course. And you can do some fairly complicated things. So this was using C# on a Windows platform and using RoboRealm for the vision tracking. And then using that algebra that I showed you, the matrix algebra that I showed you, to compute the angles at the 2 shoulder joints that were required to move the arms into position. But by the way, that's when Pi was obviously a little younger. He's a little shorter. And as you can see, it actually works pretty well. And the moment he grabs the green balloon, I have him change tracking to the red balloon. So RoboRealm has a set of variables where you can just say change to a different color. So now he's holding on to the green balloon but tracking the red balloon. And that goes on for a while. I won't bore you with the whole video, but this is my only video on YouTube that ever became popular. And by that I mean just more than a few hits. And the only reason it did, it was really funny, is because it's something I had no intention of doing. I think the title was "The Greedy Robot Wants the wants the red balloon but can't let go of the green balloon," or something. And it was just weird because all I was trying to show is that you could change the attention from red to green in mid-stride. Okay, so you can do, of course, inverse kinematics and arm tracking outside of ROS, but that was with just 2 degrees of freedom. So I've stolen this really cool slide from Tully's, and it's actually, I'm giving Tully all the credit, but of course, because that's the only name I could remember at the moment. But we've also got Eitan and Wim, all three, of course, big names at Little Garage. And this is just a neat little picture because it shows you on the PR2 all the little different frames of reference that you would have to track on your own using some kind of matrix geometry or quaternions if you wanted to know where each joint was relative to each other joint. And you really have to know that if the robot's going to interact with objects in the world. Even if the robot just needs to scratch its nose, it needs to know how to get the finger up to the nose. The first thing you do to make use of the transformation library, the TF library in ROS, is you build a physical or a virtual model of your robot. And this is actually a bit of a painful process because you just edit a big XML file. At least that's the only way I know how to do it. I think there are tools for going from some CAD drawings to the XML file or something similar to it. But in any event, you only have to do this once. So you get a ruler out, and you measure the length of the segments of your arms and your head and your servo dimensions, and you put it in. And as you saw, you then get a virtual model of your robot that you can view in RViz and rotate about. But more importantly, here's a portion of that file. It's about 6 times longer than this. But really all it's doing is giving the dimensions of the boxes, in my case, of the base, and the lengths of the links in between the servos. And then, and this is where all the magic happens. The transformation frame library, the TF library, all combined with one other node called the Robot State Publisher, can then give you the full tree. And I'm going to blow this up into a PDF and just scroll down. Up here is the base link. So the base link is the very bottom of the robot. And you can see here is the base laser joint, meaning the laser on the front of the robot. And we see that there's a link in between them showing that there's a displacement of 18 centimeters forward from the center of the base, and it's not rotated either way. And if you scroll down this tree, you get to see the whole shebang. So this is every joint in this robot, every link mapped out for you by the transformation library in conjunction with your model of your robot. And so once it's done, and now you can know where every joint is relative to every other joint as it moves about. Arm navigation, this is also just brilliant, and I don't have anything of my own to show you. So I'm stealing a little video from Willow Garage, and this is Ion Sukan, and he's demonstrating here how you can do inverse kinematics with constraints, meaning we don't want the arm to run into itself. We don't want the arm to run into the robot. We don't want the arm to run into the table. And this is just tremendous. One of the things you can do with the transformation library is you'll notice the robot's holding a stick, and it's pulling it through a very narrow gap. And we do this all the time. In fact, I was thinking about this the other day. Think about when you're using a screwdriver to screw in a screw. You almost instantly project your sense of tactile sensation to the end of the screwdriver. Our brains are just automatically able to incorporate a device, in this case a screwdriver, into the joint map that is your arm. You have no trouble doing that. Well, the TF library does exactly the same thing. So once you put something in the robot's hand, you can immediately just add that as another joint dynamically on the fly, and nothing more need to be done. If I remember right, the TF library itself is a standalone library. I mean, isn't that right? You can use it on its own. I don't know how you do that because I've only used it within ROS. And finally, the point cloud library, again, just something I wanted to point out because it's a big component of ROS. It's a big feature if you get through to learning how to use ROS, and it's just not something I've played with myself, but I'd love to. Because this is the whole three-dimensional perception, world of three-dimensional perception. So now instead of just two-dimensional images that we typically process through web cameras, we're now going to assume that we have some kind of scanning laser cloud, or now with the Kinect You don't even need that. $149, you can have a three-dimensional point cloud, as it's called in ROS, and that simply means that at every or the most points in the image you have a number of values, could be RGB values, but also particularly a distance value away from the perspective of the camera. And in this library, you can do things. First of all, you can simply visualize these objects, as I've shown a couple here, again, stolen from one of the Willa Garage web pages. And 3D feature extraction, surface reconstruction, object segmentation, and 3D object recognition, because 3D object recognition is one of the hardest things to do in computer vision, of course, because depending upon how this hand is oriented, it looks extremely different to a two-dimensional camera. All these projects, they're certainly not done and shrink wrapped and ready for everybody to use magically, but they certainly have come a long way, and they're there and ready for you to explore. So finally, just I wanted to leave you with a few resources. ROS.org, the tutorials are there, and there are more than just the beginner tutorials. The beginner tutorials get you through the basic concepts, but then there are particular tutorials on the transformation libraries. There's a really good set of tutorials on the whole navigation stack, which is about SLAM and so on. It's pretty complex, but you go through it step by step, for me, 3 or 4 times, and you finally get it right. It really helps to have a robot, or at least a simulated robot, to test it out. And then there are a handful of, one thing I wanted to point out is definitely use the search box on the ROS.org site. It's actually really good. I mean, for example, to get that list of hobby robot type controller cards today, that's all I did. I plugged in Arduino and I plugged in Roboboard, and immediately takes you to the package if it exists. And if it doesn't exist, chances are it's not supported yet, at least not in the main repositories. And then there are a number of mailing lists which are unbelievably helpful. The ROS users is the biggest one, followed by ROS Connect and ROS PCL. And it's because this is international, there's always someone there to answer your question at 24/7. It's just amazing. And then the other really cool forum is the Trosum Robotics forums that many of you may already know about. And in particular, as I said just a few weeks ago, we created a subforum for ROS-specific questions. And the nice thing about that particular forum is it's just us hobby guys hacking it out without fearing that we're going to make fools of ourselves in front of the real ROS guys. So it's a good place to go. And that's it. Thanks for coming.